Hey everybody, so welcome to the UTC plus 10 hour here for the worldwide user group meeting. Thank you guys for spending a little bit of time. This particular section is going to be around fluid dynamics and aerodynamic analysis. I think UTC plus 10 is the time zone for Sydney, Australia. My name's Omar Zohni. I work for Dassault Systems. I'm one of our simulation nerds. Really excited to be presenting. I am coming to you from San Diego, California. I am going to be acting as crew chief and driver. So I don't know if that's good or bad for you guys. A little bit more difficult for me, but you guys are going to get to listen to me, both present and kind of walk through some of the simulation techniques. We're going to be utilizing the concept designs that were developed in XDesign on the platform. I'm going to really focus on platform capabilities. So the stuff that's available on the 3D Experience platform, we have a relatively new product called Fluid Dynamics Engineer that can do some really, really powerful aerodynamic analysis. It gets rid of a lot of the limitations and the computational time associated with running analysis in SolidWorks flow simulation on the desktop, not taking anything away from the desktop products. They're very, very powerful. But the ability to utilize cloud computing for some of these analyses is a real compelling advantage. There's also some meshing advantages to using Fluid Dynamics Engineer. So without any further ado, I am going to get started with my presentation. Again, my name's Omar Zohni. I would encourage you guys to utilize the live chat. If you've got questions, please enter them there. I'm going to give you guys my email address at the end of this presentation. I'm kind of responsible for a lot of the worldwide activities around these Simulia products. So if you have questions, please feel free to send me an email. I love engaging with customers. It's kind of the highlight of my job. It certainly beats, expense reports and a lot of internal meetings. So give me a reason to not have to be on internal meetings and give me a chance to engage with you guys. I think you guys are going to be real happy with what we're presenting. There's a lot of compelling content over the day here. And again, thank you guys for being on this particular portion. And let's go ahead and get started. All right, guys, so let's go ahead and get into this. So again, the content for this particular hour is going to be around aerodynamic analysis and using the computational fluid tools on the 3D Experience platform. Again, my name's Omar Zohni, coming to you from San Diego. I think we're in UTC plus 10. So if you're in Australia, greetings from the west coast of the US and sunny San Diego. So just a brief agenda. A lot of the simulation tools on the 3D Experience platform are kind of new to our SolidWorks customers. So I want to spend a little bit of time talking about next generation simulation for SolidWorks users. We're going to then talk a little bit about some of the concepts that the very talented designers developed using XDesign, which is a product on the cloud, a CAD product completely on the cloud developed by the Dassault Systems with a lot of input from the SolidWorks brand. It's a complete cloud tool. Talk about taking those concepts into Fluid Dynamics Engineer, setting up and running the fluid dynamics or running the fluid analysis to extract, drag forces, lift forces, looking at things like pressure and velocity and figuring out, which design, using simulation to really figure out which design is best. And then we'll discuss a little bit about what's next. So let's get into next generation simulation for SolidWorks users. Now, what I want to point out here is that you're probably aware of SolidWorks. I'm sure you guys are aware of SolidWorks, right? So SolidWorks is a brand inside of Dassault Systems. Another brand inside of Dassault Systems is a brand called Simulia. And Simulia is responsible for the development of all of the simulation tools that Dassault produces and develops, right? So even the desktop SolidWorks simulation products, the plastic injection molding, the plastic injection product that SolidWorks has, are all fall under the Simulia brand. What also falls under that brand is, if you're on this call, you've probably heard of Abacus. It's a arguably best-in-class finite element analysis software, really good at doing explicit dynamics, really complex contacts. But what you'll see is there's also products for magnetics, for computational fluid dynamics, for durability, for plastic injection molding, topology optimization, um, system modeling. The commitment to simulation at Dassault runs very, very deep. And to our disadvantage, well, let me get to that in a minute. So if you kind of break up simulation into their 8 basic building blocks, what you'll and if you ask a dozen engineers, you might get different physics for these 8. But what you'll see is that Dassault has a solution for pretty much any type of physics. And again, that solution comes from the Simulia brand, right? So, whether it's durability, fluid dynamics, electromagnetics, there's probably a solution that Dassault and specifically Simulia has. Now, if you take a look at kind of what was going on at SolidWorks, we have kind of always broken up or created simulation products on the desktop that were really geared towards designers, maybe into the engineering space. But if you were doing really complicated multi-physics, really complex contact, really ill-defined contacts, large deformation, high plasticity, things that were typically for the analyst, SolidWorks Simulation Premium kind of broke down, right? And what we realized was that we were doing ourselves a huge disservice by not leveraging the capabilities that were available from Simulia. So a handful of years ago, what we decided was, hey, rather than trying to continue and improve SolidWorks Simulation Premium, and that doesn't mean that we're not getting rid of bugs and we're not still making incremental improvements, but rather than trying to make that nonlinear solver better or develop, kind of push SolidWorks flow simulation, we needed to leverage the capabilities that were inside of the Dassault family, and we're doing that on the 3D Experience platform. And there has been a lot of collaboration between the SolidWorks brand, the Simulia brand, the Innovia brand, the CATIA brand on the 3D Experience platform. And that's where we're going to be spending, I would assume, a lot of this. Probably the day is going to be around capabilities that are available on the platform, because that's really the future for Dassault systems. That doesn't mean desktop SolidWorks is going away. It doesn't mean desktop SolidWorks simulation and plastics and flow simulation are going away either. They will remain. But a lot of the really compelling enhancements moving forward are probably going to be on the platform. And that's just the direction that Dassault has made. And I think it makes a lot of sense. And there are also so on the 3D Experience platform are kind of these 2 blue sections. We also have some legacy products that are available from Abacus, and we'll talk a little bit about those. So, I think you guys have probably heard a little bit about the 3D Experience platform. When you look at it for specifically for simulation, it's going to be the place where all of these different physics solutions start coming together, having the ability to collaborate, share, transfer simulation results from one physics to another to really start doing multidisciplinary and multi-physics type simulations are going to come to fruition for Dassault. I'm sure you guys have heard this, I just kind of want to reiterate it real quickly. What are the compelling advantages of the 3D Experience platform? Here are a handful of them, right? So it's on the cloud. It reduces a little bit of that IT infrastructure. If you're doing simulation, the ability to offload that simulation and run it on the Simulia cloud is very, very powerful, because you're going to be running on multiple cores, whether it's 8, 16, 144, all the way up to 144. You're going to be able to leverage cloud solutions, and that Simulia cloud is really, really written, or the Simulia cloud, the hardware is really, really built to handle simulation, right? It's integrated, so pulling your model in from SolidWorks is very, very easy, whether you're using the UES approach or you're using a direct import. It also gives you the ability to do parametric design and drive your SolidWorks model. So that's a capability that was introduced in the last couple releases. It's very, very powerful. I'll show you a couple examples of that. It also allows you to really collaborate And I think in the last, however long COVID has been around, it seems like it's been here forever. But, in the last 18 months, the ability internally to utilize the platform to collaborate with our colleagues all over the world I really think has pushed the SolidWorks brand to start leveraging the 3D Experience platform much more effectively. Now, if you're, I don't want to spend a lot of time here, but if you're considering structural analysis, there are a handful of products that are available. I would say kind of like the good, better, best, and then there are 4 flavors of that basically. So you're doing linear analysis, structural designer, the structural engineer. In addition to these, physics also turns on some more advanced meshing capabilities. I would argue that these 2 are probably the ones that SolidWorks users are going to benefit from most. So durability performance engineer turns on fatigue analysis, both strain and stress life, and it uses all of these are using the Abacus solver, right? But the real compelling features of the Abacus solvers are the way that it handles meshing, advanced material models, as well as contact. And then durability mechanics engineer, there are a couple things that it adds that performance engineer doesn't. I would argue probably the key feature is the explicit dynamic solver, which is what is being used to solve that fan blade model there, and the ability to do like element birth and death. It also has a really powerful material calibration app. So these are just some of the types of analyses you can do on the structural side. And, some of these are ones that maybe you could have solved with the SolidWorks desktop product, but certainly, like, you're not going to be able to do a bird strike analysis here because we're utilizing what's called SPH elements, smooth particle hydrodynamics, to capture the behavior of the bird. The bottle crush with with liquid crush, you're not going to be able to do that. Bottle with liquid drop. Some of these really, really complex impact and drop testing, element birth death. Again, these complicated contact models, one of the real powerful features of the Simulia products is that it can handle, the way that it handles contact in general is that it makes the assumption that all faces, whether they're initially touching or not, are potential no penetration contacts, right? So you don't have to set up contact pairs. Now you can, there are some ways to automatically bond bodies if that's something that you're interested in. The ability to there's a really nice physics results explorer that allows you to look at results. Here we're taking a look at the parametric study app. So if you pull your model in from SolidWorks and you've got parameters, you can very, very quickly set up a parametric study where you flag the parameters that you're interested in studying. You can specify the range that you want those parameters to vary from. You can obviously set up multiple parameters here. I think we picked 4 or 5 different ones. You can specify the output that you're interested in. Oh, so we're also varying a shell thickness here. Very, very easy and intuitive to set up these parameters. You can see all of those different input parameters. We can flag our response variables. So those are the output parameters. And I'm showing you this on the structural side. We're going to have a video that also shows it on the fluid side, but the setup is basically the same. And once we've, specified our input and output variables, we can specify objectives for those variables if we're interested. So in this case, I'm saying that I don't want the maximum stress to be below a certain value or above a certain value. I'm saying that, I'm targeting the displacement, saying I want to minimize the mass. And we get a really nice kind of rain flow chart that shows all of the different design iterations. And again, this can be done with a SolidWorks model very, very easily. It's going to show you, the configurations that are feasible, the ones that are not feasible. It's going to show you what the best design is. You can kind of completely customize that XY chart based on your response variables, your input variables. So I feel like this interface, it's really, really intuitive. We can look at trade-offs between the different design variables, which is what we're doing here. Really, really powerful parametric design optimization tool. And that tool is going to be available in the fluid tool that I'm going to show you guys in a minute for the particular aerodynamic analysis. Also available in mechanics engineer, so structural mechanics engineer or durability mechanics engineer. Now, if we're talking about the fluid solutions, the one that we're really going to focus on today is fluid dynamics engineer. There's also a plastic injection engineer, so if you're doing injection molding, similar to what we've got on the desktop. And then there are two kind of more kind of desktop solutions that are available from Simulia. There's XFlow and there's PowerFlow. And if you're in the CFD space, they both use the lattice Boltzmann solution strategy. So just be aware of that. XFlow, very, very good for multi-phase moving geometry, fluid structure interactions. PowerFlow, really, really highly transient applications. Aerodynamics, aeroacoustics, and aerothermal are kind of the places where it resides, and it gives the most value. So some of the different industries that you know, these solutions are implemented or being used in, and you can, you know, as with SolidWorks, you know, the industry, they're being used across a wide variety of industries, right? So I think that's the takeaway from here. Here are some different, you know, where the Simulia fluid solutions are being used, and some more specific examples of the utilization of those fluid tools. So, you know, all the way from aerodynamics to you know, nozzles and pumps, turbine blade efficiency, definitely being used quite a bit in bio and the medical field, pharmaceuticals, definitely in high tech and electronics. Yeah, we've had a couple engagements recently with some companies that are doing boat and hull design, so marine applications. Consumer products. Simulia is such a powerful brand, and again, as a simulation nerd, it's a really, really powerful time to be working on the SolidWorks team and engaging with some of these Simulia products and the team at Simulia. They're a really, really great and highly educated, highly informative team. Some more mainstream applications for fluidics. You know, and everything from tube squeezing to engine thermal analysis, so conjugate heat transfer there at the bottom for electronics cooling, drug delivery, flutter analysis. Lots of really, really great applications. So the takeaway here is whatever industry you're in, whatever problem you're trying to solve, Simulia is probably going to have a solution for you. A little walkthrough of a parametric design utilizing flow simulation. This is a real simple example of just flow through kind of a ducting kind of model. So really, really nice to be able to look at results for a lot of those different simulations. Some more advanced applications. Some of these are using some of those XFlow and PowerFlow computational fluid dynamics solutions from Simulia. We also have an electromagnetic solution. I'm not going to spend a lot of time here, but if you're interested in electromagnetic analysis, please reach out to myself. I'll give you guys my email in a couple. At the end of this presentation, you guys can feel free to email me. But again, whatever analysis you're trying to do, it's quite likely that we're going to have a solution for you inside the Simulia product. So if you're looking at kind of the differences between the desktop solution and what's offered from Simulia, you guys can see that the Simulia offering is, there's just a lot more on the Simulia side. If you're interested in more information, just go to solidworks.com, products, 3D Experience Works simulation, and you'll have a ton of information about the products that are available. All right, so a little overview of what's, you know, coming and what's a bit kind of the next generation simulation tools for SolidWorks users. Now let's go ahead and talk about some of the concepts that we've got for our car design from XDesign. Okay, so I'm assuming you guys have seen the design. So I'm not going to spend a lot of time here, but CAD on the cloud utilizing XDesign, what a powerful new tool that's been developed completely on the cloud. You know, the ability to kind of just drag and pull surfaces to create some really, really compelling shapes. You can see all of the different designs or concept designs are shown right here. Even a little bit of fun here with the slug, and we'll do a little bit of aerodynamic analysis on that one too. So we're gonna have some fun. So you've got the model here in X Design. I'm not going to go over, you know, the decisions that they made to kind of come up with these designs. But basically, with the, you know, we can take a little bit more granular look at all of the different designs. Some really, really cool models. Very kind of Batmobile looking. So what we're going to do is we're going to walk through and we're going to run some computational fluid dynamics on analysis on these, right, to figure out which one is the best. Maybe give them a little bit of design guidance, right? So I think those are the 6 designs we're going to be working with. But, you know, so we're sitting here in X Design. How are we going to get that over to Fluid Dynamics Engineer? And really, this is one of the real compelling features of the platform, right? We're sitting here in X Design. We've got our geometry. I can just click on the compass and pick the app that I want to open this in, whether it's structural analysis. In this case, I'm going to pull it over into fluid scenario creation. And that's really all we need to do. So once we've got it in Fluid Dynamics Engineer, let's walk through what the setup looks like and do a little bit of post-processing. So here I am sitting in Fluid Dynamics Engineer, right? So first and foremost, there is a very, very powerful assistant that we can utilize. Now, I've already set these up. I've actually run these analysis, but I want to walk you through what it would look like from start. So first thing that we're going to do is we are going to specify we're going to create a finite element rep. So the finite element rep is kind of where the finite element model resides. I'm going to, again, I'm going to really leverage the assistant because even I've used Fluid Dynamics Engineer now for 6-9 months, and I still feel like the assistant is the best way to really set up your model. So depending on the type of analysis that you're running, you're going to have to go through a little bit of model setup. Now, the model setup would allow you to specify kind of if you're running an internal analysis, what parts you want to keep, the material properties, your mesh parameters, you know, the bounding box. In this case, you know, we're not really doing, we're not gonna use the model setup feature in the assistant for this guy, but you can see kind of some of the settings that are available there. I'm going to hop right into the fluid domain, and I'm going to individually set up each one of these cars, right? It's not going to be like a race where there's one behind one another. And I'm just going to pick that initial part and say, look, this is the part that I want to utilize in my analysis. Now, what are my exterior boundaries going to be? So let me just go ahead and say that for this particular model, I am going to use a bounding box, right? So basically, we're going to make the assumption that this thing is kind of inside a wind tunnel. And you can see the dimensions of that bounding box. Again, I'm not including any of the cars behind the first one. So for my bounding box, I'm going to have to kind of compress it a little bit, or I'm going to kind of customize the size of it, right? So, and because we're not including the wheels, I'm going to pull the bounding box up so that it's just above kind of the bottom surface of the car body, right? So I'm going to pull it down, the top down a little bit, move the back in a little bit, and maybe definitely pull the left and right sides in, right? We don't need that much. Now, the size of the bounding box is something that's really important, and as you run more and more of these kind of computational fluid dynamics analyses, you'll kind of get a feel for how big your bounding box should be, because the larger you make it, yes, the more accurate your results are going to be, but also the more computationally expensive it's going to be. And I believe I made a mistake there. That maximum X should be 4,500, right? So it's kind of centered around the Z, or X equals 0. Now for my Y, I'm going to just kind of round the numbers that were there. And then for the Z, that kind of the negative Z value, play with it a little bit. That should be fine. And I'll kind of round off the top. So that all that's doing is really specifying the bounding box. Now, I need to tell the software where my fluid region resides. And it's very, very easy to do. All I'm going to do is grab one of the faces that resides on the car. And what it will do is it'll give us a very nice graphical feature that says, hey, okay, it's assuming that the fluid region resides where that box is. So outside the car, which is exactly what we want for a fluid dynamics and external kind of aeroflow analysis. For my surface selections, really don't need to do this unless there are specific surfaces that you want to grab results for. In this case, because I want to grab lift and drag results, I am going to grab all of those surfaces. And I could have given it a more custom name like surface selection one. A lot of times people call this the wetted surface. And now basically my fluid domain has been set up. Now I can kind of walk through the assistant. I need to give the fluid section some properties, right? So properties are basically what is the fluid that this thing is going to be sitting in. And, for this analysis, it's not like it's underwater. We're hoping that it's not underwater. Although if it's the Batmobile, I guess the Batmobile could go underwater. But in this case, we're going to make the assumption that it's air. And really, that's all I need to do for the model in this case. So for a problem like this, really quick setup for your model. Now, the next step is going to be specifying a procedure. So I'm going to specify what physics behavior I want. I'm actually going to leave it at the default. I should point out there are way more complex turbulence models that are available. So it's not just K epsilon. There are a whole host of turbulence models that are available. And I'm just going to kind of leave the default settings for my steady state step. So I'm not going to run this transient. I definitely could run it transient. But in this case, I'm not going to. Now, what are my velocity input, or what are my boundary conditions going to be? I'm going to make the assumption that for all these, we're going to look at 100 mile per hour vehicle speed. On the backside, I'm going to say that there's a pressure opening. And then for kind of all the walls around it, I'm just going to say that it's a symmetry boundary condition, right? And that's typically how these guys are modeled. And honestly, guys, that's all I need to do for the setup. Now, because I know that I'm going to be requesting some output, like I want my drag and my lift forces for this, I'm going to go ahead and say, look, I want to create a custom output request, not for the whole model, but just for the wetted surfaces, right? So I'll go ahead, grab one of the surfaces, say that I want to propagate by tangency, and that will grab all of the surfaces that will grab all of the surfaces that have some tangency to the initial one. And I'm going to say that I want some history data. So it's not like I want pressures on the surfaces. I actually want the sum of the forces on those surfaces. And because there are quite a few surfaces, I think there were over 200. It takes a second here for it to grab it, but there we go. So I've specified my output request. Now, again, lots of bells and whistles available for meshing. Typically, for external aerodynamic, you use a hex dominant mesh and you specify some boundary layers. So that is exactly what I'm doing here. I'm saying that I want my maximum element size to be about 250 millimeters, my minimum size to be 25, and then I want 4 layers of boundary elements, with the first layer being 0.15 and then going up to the minimum element size. Now I'm going to come to the Simulate tab. I'm just going to click Model and Scenario Checks, because this will generate the mesh and make sure that my setup is adequate. And I want to be real clear here, guys. This is kind of a fun example. I'm not like I'm not really designing a car. So, if I were, I would definitely want to do like a mesh convergence study, make sure that my results were adequate. I would probably, let's take a little cut plot here and take a look at kind of what the mesh looks like right around the car body. Let me set it so that it actually shows the mesh. So zoom in here a bit. So you can see those boundary layers and the way that it transitions from a nice small boundary layer all the way out to the relevant element sizes, right? And this is a hex dominant mesh. It's not a full hex mesh. So our mesh seems to be great. Our simulation checks were valid. Let's go ahead and simulate this now. Now, another real compelling feature of Fluid Dynamics Engineer is that out of the box, if you purchase this product, you can run on 16 cores locally or on the cloud at no cost, which is very, very different than a lot of our competition, as well as what flow simulation can do, right? So, and when I say 16 cores, the way these solvers are written is to really leverage multiple cores. So if it takes 16 hours on one core, if you're running it on 16 cores, it's going to take about 1 hour, right? Now there's a little bit of trade-off with, or a little bit of degradation as a result of data transfer, but I'm actually going to say that I want to run this on the cloud. And when you run it on the cloud, again, you can run it on the cloud with 16 cores at no cost, or you can utilize more cores, which come at a cost. So, you can do 16, 32, or all the way up to 144 cores. So a really, really simple guided workflow. So now let's get to the post-processing. All right, so when the simulation finishes, we can go ahead and start post-processing. So I'm going to walk you through, there are tons of different ways that people will probably post-process a simulation. So I'm going to first start by looking at the velocity. And I'm just going to take a cut view. And you can see I can go left side of that cut plane, right side, or I can just look at, an individual face on the cut plane. So these are the velocity vectors right on the cut plane. There are really quick, easy ways to kind of orient your view. So in this case, I believe the view that we want is back, but we can kind of walk through. So, there's our bottom view. Our left and right views are also available. The one we're interested in, oops, sorry, I meant to hit bottom there, or back there. So there we go. So there's our back view. Fluid is going to be coming from right to left on the screen. So you can see we can take a look at velocity vectors. Kind of a busy plot. We would probably want to orient that or do maybe a cut plane. Let's go back to the velocity. Now, you can see, as we expect, right, you got 0 velocities on the car. What is interesting, though, let me pause here for 1 second, is you can see you've got a negative velocity. So negative velocity typically means a high pressure area. So this wing, I'm not a car guy, I'm assuming this is a wing, it's kind of not doing what is expected, right? Because if we've got a high pressure region here, the wing is supposed to be driving this car down. High pressure is insinuating that it's creating a lift, right? So probably not doing what we intend. Let's go ahead and look at the gauge pressure. Yeah, and that's exactly. So we're seeing kind of a high pressure here, also a high pressure here. So this is causing this a bit of lift. So not what we would want from a wing. Definitely not what we'd want from a wing. So let me just turn on the car real quickly and let's take a look. So I'm going to go ahead and say that I want to select the surfaces. I'm just going to select the part, which is basically, in this case, it's the car. And we can take a look at the pressures on the car, right? So this is going to give you an indication of where you've got high pressures, where you've got low pressures. If you're a car guy, there's a lot of information that you can extract from these types of plots. Let me turn off that cut plane. So high pressures on the front end, you kind of expect that. Might make more sense to have more of a flat surface there on the front. Real easy to kind of generate streamlines. So I'm going to use this rake feature and say, look, I want 25 streamlines across the car in that direction. The streamlines will go front to back. I'm going to thicken them up a little bit. And okay, that's not really awesome, but let's create a few more. So there's some automated approaches that you can use. I tend to like using this rake feature because I think it kind of gives you a more compressed group of streamlines, right? Like I don't want to just see the streamlines that are way out in space. I really want to see what's going on close to the car, right? So this is a perfect example, right? We can see some recirculation that's going on kind of at the side of the cars, or the side of the car, that the side of the body. Let's maybe spin this around and create some on the back end. And you know, again, these don't have to be kind of these lines. You can also create arrows, and let's add a couple more. I think if we add them here on the back end, we'll get some nice visualization. It's taking them. Yeah, there we go. So maybe just one more, a couple more sets. Right, so we can get a real nice feel for how fluid is moving over and around the car, right? Areas of recirculation, which are important, kind of dead zones. You know, again, we can look at pressures. So a real nice way to kind of visualize what's going on around the car using streamlines. And again, there are probably some more automated approaches as you start getting. I'm not an expert at FMK. I'm playing one here or in car design. So let me hide those streamlines. Show you guys a couple more things here with respect to post-processing. So another really important thing, right, is going to be the lift and drag forces. And we can really, really quickly get those by using a sensor. So I'm going to say, look, I want a sensor, which just like on SolidWorks when you're doing simulation, I'm going to use the history data and grab the Y and Z direction, or so let's start with Z. Z is obviously lift. And that's going to be the vector component in 3 direction. Let's look at most the maximum and last. It's a steady state analysis, so really we're interested in the last. That should be the converged step, but the maximum and last should be pretty close to one another. All right, so lift forces. So we can see what our lift forces are, and they are 50. Is that 52? 529,000 newtons. So that seems pretty high to me. It's in the negative direction, so it is pushing it downwards. Let's also look at the drag force. And that's going to be vector component 2. Again, we'll look at maximum and last. And about 7,000, so negative 7,000 for drag. So that's the force that's being put on the car. All right, so that's for this particular concept. Well, that's great for one concept, but obviously we're going to want to look at the other ones, right? So once we've set up the first one, it's very, very easy to duplicate that. I'm going to say I want to duplicate the analysis case, and then all of kind of our setup and our post-processing is already going to be defined. All I need to do is go and redefine my bounding box, right? Because it's going to, not all the cars are sitting in the same space. If I was going to make a suggestion to our designers, I would say, look, let's make sure that all the cars reside kind of in the same space. And that would make this a lot easier because we're not going to have to be sliding the bounding box back. We can ensure that the bounding we can ensure that kind of everything remains the same across all of the different designs, right? So that would be something I would kind of suggest for our designers. Let's make sure all the concepts sit in the same space. So let's now kind of take a look at comparing the results of some of the different. So now we can really use simulation to guide the design. And again, all of this stuff is really automated, because once you set up my suggestion would be set up your first case, make sure that all of your pre-processing, all of your output has been adequately requested, and then just create copies of those cases, because then, it's going to minimize the amount of setup that you have to do on the other ones, right? So here we're looking at gauge pressures for the 6 designs. I would assume that you probably, this guy, I think it's number 5, actually probably looks, with respect to pressure, I would say that's probably the best, because you can see it's really pushing that front side down. You've got a higher pressure here on the wing too, which is going to be pushing that down. And then I think these two are kind of balanced out, it looks like, a bit. So that to me looks like it's probably the best design, although again, I'm telling you, any of these ones where you've got like a high pressure kind of on the downside, that's going to be lifting the car up. You certainly don't want this thing to fly, right? So it looks like probably design number 5 is the best. Probably could do a little bit better with the wing to get the backside pushing down. You'd really like to see, I assume, a higher pressure kind of on the top side of the wing. And again, the goal, like I said, I'm not a car guy, but I think you guys can see the design, what we can do with kind of these simulation tools, right? We can kind of guide the design, come up with the best body design, potentially what the best wing design is going to be. We can also look at, the velocity and how the velocity is moving off the car. I'm sure to a car guy, this data is going to be very, very important. We can also look at streamlines, also look at, the sensor data for lift and drag force. That's probably where you're going to get the most information. We can get real granular and just look at the lift and drag data just on like the wing or just on certain sections of the car. So we can really drive the body design by looking at different sections, and if they're performing good, maybe look at the front section, the mid section, the back section, the wings, all that type of stuff. So really, really powerful way to explore your design and provide some feedback to your designers. And the nice thing is these simulations are all linked to that X design model, right? So if I make a suggestion to my designer and he goes and changes one of the concepts, I'm going to get a flag in Fluid Dynamics Engineer that says, hey, this is out of date. The results are out of date. Do you want me to rerun it? All very, very automated and controlled and precise, and removes a lot of the redundant work because we're doing it all on the platform, right? And really, really leveraging some best-in-class capabilities across the SolidWorks brand, across X Design, across Simulia, utilizing cloud computing. Really, really, it's just, like I said, I'm really excited. It's a great time to be here at Dassault Systems and working in the simulation space. So, just for a little bit of fun, I went ahead and ran some analysis on the slug. Since we're doing a SLUGME meeting, you can see that slug is getting a lot of pressure at 100 miles per hour on its face. So it is probably not feeling its best. It's going to have a sore neck for sure. And it might lose an eye. It looks like maybe one of its eyes are going to pop out of its head. All right, so what's next? So first of all, if you guys have questions, I'm going to leave this up here for a second. I had a lot of fun with this. The team that worked on this is an absolute delight. Some really, really great, fun guys to work with that are just real professionals in their space. And just, they love the SolidWorks brand. They love DS, and I feel real honored to have worked with those guys, both the internal team and the external team. So again, you guys have questions, feel free to send me an email. Like I said, I love engaging with customers. Kind of the highlight of my job is engaging with customers. It beats a lot of the internal crap. So feel free to send me an email. What's next? Feel free to visit the SWUGN, so SWUGN.org. Find a group. We're doing this one virtually. I think there are some live user groups that are starting to happen now, although I just did another virtual one last week that was here in the US. Hopefully COVID passes and we would all like to be in front of one another. I think that's kind of where the best exchange of ideas happens, when you're, sitting around breaking bread or having a beer or a drink, a soda someone. It's nice to be able to look someone right in the eyes and get a feel for them. If you're interested in becoming a leader, reach out to I think Dan Wagner is handling that. But again, great pleasure to present this stuff. I hope you guys found it useful. Please feel free to reach out to me if you guys have any questions. And I'm going to kick it back to our crew chief, which is also me, for a little bit of an outro. All right, guys. Well, hopefully you enjoyed that. This is your crew chief here. I hope you enjoyed the driver. I thought he was fabulous, but I'm probably a little bit biased. I'm not going to spend a lot of time here. You guys have my email address from the presentation. I'm just going to kick it back to the race broadcast team, which is broadcasting live. So that's Dan, Todd, Eric, and Cam. Great group of guys. Again, any questions, please feel free to reach out for me. A lot of fun presenting this. I hope you guys got some value from it, and I look forward to engaging with any and all you guys. Enjoy the rest of your SLUGME day, and hopefully we'll be in touch. Cheers.